I will launch right into a lecture today on quantum computing. I think that those of you in the audience, represent a great diversity of backgrounds. So I'm going to also hit a diversity of topics. So here's my outline for today, but I will leave plenty of time for discussion at the end. I will begin with what I consider the most essential thing to know about what is a qubit and how it is distinguished from a bit. And so that will be a small tutorial about that. And you may wonder, what do I feature as the most important thing about a qubit? Well, you'll see it in a moment. Then I'll jump right to the present and show you maybe my favorite quantum computer of today, which may be a completely different one than the quantum computer of next year, but is worth looking at and trying to understand some of the features that have emerged. For many years, quantum computers were just a dream, and we were often criticized for saying, well, you keep saying it's 20 years from now, and then another 5 years later, you say it's 20 years from now. But now I can say, yes, in fact, we have quantum computers, but we'd like to have better ones. So when will we have a better one? Well, 20 years from now, I guess, but I think they will actually continually get better. I will spend some time digging back into the history of quantum computers, and we'll talk about the start of quantum computing, except I don't know what year to point to, so I'll point to all of them. So here's my list of my favorite years: 1960, or is it 1982, 1994, 2016. I could say 2016 is the year that IBM put its first quantum computer on the cloud, and maybe for many of you, that's the starting point. That's the one that marked the era of real quantum computers. But for me, or certainly intellectually, the ideas of quantum computers started way further back, and including many high points over the years. And somewhere in my sort of historical story, I will tell you about those criteria that you heard about and tell you what I was trying to do when I wrote down those criteria for the first time, which, well, to give you a clue, was sort of started happening already in 1994, and were sort of complete in the year 2000, but they're not maybe the most important aspect of the timeline. Okay, so now I'm going to begin with some really basic stuff, so I'm sure I'll bore some of you, but I hope that it's at least a little bit interesting and a little thought-provoking also for a few of you, even experts. So we talk about computing, and at least for the last 100 years, when we talk computing, we mostly talk about binary arithmetic, and we talk about, therefore, information represented as one of two states of some object, call it 0 and 1. And now we recognized, although I'll point out it was not even so obvious in the timeline until rather long along the timeline, that the most essential thing that you wanted to do to introduce quantum mechanics into the story of the bit, into the fundamental information carrier of digital information processing, is promote it to an object from which you can build a wave function. And so that if you have just a single bit, you should be able to make states which are not 0 and not 1, but which are, as we say, superpositions of those two with some coefficients, some actually complex valued coefficients A and B. So we say that there's a physical reality to saying that a system is in a definite quantum state, but which makes it indefinite from the point of view of whether it's a 0 or a 1. And the point I will make is that with a small sort of Gedanken experiment is that it's not merely that it's sort of unknown whether it's 0 or 1. It's a much more definite state of knowledge than that. So let's do this by imagining that we're representing our physical, let's say, bit of information with whether a single particle, I do say single electron, and this is a qubit that we've thought about over the years, but do not find favorable. It does not have really good characteristics, but is conceptually a perfectly good qubit, where we say the 0 and 1 of this single electron is whether it sits in the left side or the right side of a bistable potential well. As I said, there are so-called charge qubits, which still play a little bit of role, but which were long ago displaced by spin qubits as a favored single electron qubit. Okay, so, well, we do have the situation as the digital computer engineer would want it, single electron on the left, 0, single electron on the right, 1. So what about these other states, these alternative states? So the way I describe it here, and it was Deutsch who actually really articulated this very precisely, He says, to get to quantum mechanics, you have to think about first the idea of randomizing, paradoxically. And so you may want to bring the system into a situation where it is neither a 0 nor a 1, but in some sense a 50% 0 and 50% 1. A conventional regular computer engineer would know what this means also, because if you make a hardware random number generator, you do things exactly like what I'm describing here. That is, you have a bistable system and you put it in a condition where it doesn't know what to do. Or the way I've described it here is, suppose you start it in the 0 state, but you do something to make it less definite, which is, for example, to make the barrier lower. And then you would often say, well, you make it so low that even thermal excitations will cause the system to bounce back and forth between 0 and 1. But I won't follow that track very much, but I will just say that for whatever reason, lowering the barrier will give the system some chance of departing from the 0 state and actually ending up in the 1 state. And suppose that probability of doing that is 50%. So you could say, and you do in fact say in a hardware random number generator, that that's a good way of producing a random bit. But from the point of view of quantum mechanics, is this state really random, one might ask? But now we have to indeed discuss more of the physical process that's involved in going from the 0 to the 50-50 case. And what we will say will be more specific here and say that that is going to occur because of tunneling, because of electron tunneling, and therefore because of a purely quantum mechanical phenomenon that particles can indeed penetrate through walls, can pass through regions where they're forbidden to be by the laws of classical physics. And so you can indeed lower the barrier. I show this sort of dotted version of the barrier, lower it enough so that indeed tunneling can occur, and then it can bring itself into this 50-50 state. Now, I see I already jumped into the punchline. I should have stayed on the last slide, because what's really very different about quantum mechanics is that you can prove that this apparently random state that you end up with is actually not at all random. And you do it by performing or continuing the thought experiment in the following way. That is, you lower the barrier once, let it get into this 50-50 state. You raise the barrier again, hold it stationary for a while, then you lower it one more time. You try to make it, quote, even more random, but instead it sort of completes its quantum tunneling and it ends up definitely in the 1 state. So we say this superposition of 0 and 1 is not at all random, because I do something to it which from a classical point of view would make it even more random, but in fact it definitely makes it actually less random. It sort of completes a process and turns it into a 1 state. Now, this process of flipping from 0 to 1 is Boolean logic, what you call the not operation. And so what I've described is something which you do twice to get a not operation. And so we refer to this as a square root of not, as a logic operation. And basically this, with ordinary Boolean logic, the ands and the ors of ordinary Boolean logic, is enough to give a whole new type of logic, which is the one based on quantum physics. So I featured this 1 particle, 1 bit superposition as the sort of key new feature. You would often say, well, but surely the new feature is entanglement. But I would say this plus ordinary computer logic inevitably gives entanglement, which is just 2-bit entanglement or 2-bit superposition states, or more than 2 bits. Once you admit the possibility of having superpositions with this sort of deterministic character, you inevitably bring yourself into the state space of entangled states and into the rich information carrier that quantum states give you, and to the essentially new software that it makes possible, the new instruction set that is made possible, that has, as is very famous, of course, high computational power, if we finally understand how to really harness it. But that indeed is still in the future. 20 years in the future, I don't know, but we're not really quite there yet to fully harness the capabilities of the quantum computers. But let me pass on from this very conceptual introduction, and that's all I'll say by way of sort of scientific introduction to the basics of information processing with quantum mechanics. And I want to pass immediately on to the here and now. So what does a quantum computer look like in the year 2023? Well, actually, I'm showing you a few things that were published in popular science in the year 2022. At this level, it's not so different. Well, I'll mention one way in which it isn't different already. I bet that most of you have seen a picture like this, and you are told this is a quantum computer. This is in fact a superconducting quantum computer, but I really have to, in a sense, disappoint you in saying basically nothing you see in this photo is functioning quantum mechanically. There is not a qubit in sight in this picture. And in fact, this picture, this is courtesy of IBM, is just the control apparatus or the physical structure that is built to house the quantum computer. I'll show you in a slide or two where the quantum computer is. It's actually out of view in this picture. And most of what you see here is the hardware that's needed to, first of all, make the device very cold. When this is in operation, there's a can over it. There's a thermal insulation can, so that the interior of this structure, in particular the lower regions, can get to extremely low temperatures, less than 1 Kelvin. And then there are many, many wires going from top to bottom, and those are the ways in which signals are brought in to control the quantum computer. But you do not, in fact, see anything about the quantum computer itself, the qubits, in this view. If you step out from this view, so here's this animation is showing a few things which I'll go through as it loops through. So a quantum computer is one where you have to issue instructions to it, which are turned into actual waveforms, which were shown briefly in that little part of the picture. And the picture that I showed a moment ago was on the right. Now it's just disappeared again. But I'm sure some of these you know quite well. That is, on a regular computer, you write a set of instructions for the quantum computer, which look like just regular, instructions of a regular programming language. There it is, like QC measure. It goes through some magic box, which is the dark blue part of this picture, gets turned into very precise waveforms. It's shown as these sinusoidal pictures as you see this looping by, but in fact, they're much more complex than that. They're usually highly tailored to do a specific job, to cause a particular operation, like a measure operation, to occur. And then a signal comes back out, which is in fact the answer to the question, at this moment, is the qubit a 0 or a 1? And then you do that innumerable additional times. If you're in the future, when we run, say, a factoring algorithm, there will be like 10 to the 18th such individual steps. At the moment, there are not nearly so many, but there are a multitude of steps. I want to say something about this dark blue region that is the region where the computer instructions get turned into waveforms. These are highly important and specialized parts of this device. And they're probably the part which is kept the most secret by the companies that are doing this. So this is IBM's very fuzzy picture of the large control rack that is needed to prepare the signals that are going to go into the quantum computer. These are all electronic devices. They're regular digital or analog, actually mixture of both devices. And there are many, many channels, basically because every qubit has to get its own channel to the outside world. It is a little different in other realizations of quantum computers in that in many of the others, there will be some optics involved, so that computer instructions, that is regular CASM instructions, or some, Qiskit instructions from the high-level language will be turned into optical pulses. That is not the case in this style of computer, which operates only on electrical pulses. Okay, so let me say a few more words about this computer. So finally, we pan the camera down to near the bottom, and now many, many more cables and control apparatuses and cables into these plugs. And the quantum computer is finally in this tiny little white region in the middle. So I didn't mean to advance quite so soon, but this is itself, and this is a region where the chip is mounted, where a chip is mounted. Let me just see if I'm going to, on the fly, turn myself into a laser pointer. Maybe this one. Okay, so that didn't work. Never mind. Anyway, so the quantum computer is just this little region, and all this work is involved in contacting to it and sending very precise information to it, and then receiving precise information out from it. Now, a view of the chip as of 5 years ago, more than 5, maybe 7 years ago, at the beginning of the IBM cloud era, was that it looked something like this. Now, I'm not going to explain extremely much about what's on this chip. It looks like a microelectronics chip, but there are some important differences. One is that the device is way less miniaturized than a regular computer chip. That is, the working devices, the actual qubits, there are 16 of them on this, are in these little square regions, 8 of them lined up along here, and 8 of them lined up along here. And they are not so small. They're nearly a millimeter across. There is a working part. These are based on the physics of superconductivity. There is a very small working part which involves the tunneling of superconducting electrons from one region to another. But it is fair to say that the entire structure, this entire millimeter-sized structure, is functioning as a qubit. Okay, so let me explain just a few more things about what has happened in the meantime to this in the years that it's been available. And I shouldn't overemphasize IBM here. I've used to work for IBM, but that's 13 years ago. And I admire their work, but I also admire the work of the Google company. I admire academic work at in Zurich, for example. I admire, however, the ion trap work of Quantinuum, but I should be careful because I would have to now name about 12 more to be fair. Instead, I'll be unfair and just stop there, but just to emphasize that there are many organizations that have done things of this complexity and definitely higher at this point. All of them have this situation that there's a very considerable classical infrastructure that's needed to take care of their quantum computer. And then there's always some unique central region where actual qubits live and are very carefully shepherded through their operations. So let me say, however, a few things more about where this goes. What is the idea? The idea, of course, is to have more qubits. There was an insight, and this is already 20 years old, that more or less regular arrays, but square arrays, that is, I should say, two-dimensional arrays of qubits, are actually quite powerful as an architecture for a quantum computer. That's partly because it's well adapted to the needs of quantum error correction. Sorry, this slide has too many words on it. I was not going to say most of these words, but just to say that already now, almost 15 years ago, at a cartoon level, it was sort of understood where this was going. In this cartoon, it was understood there should be some kind of qubits. It was not even specified which, the green dots in some kind of regular two-dimensional array. They need to have things that couple them to each other, and it was understood that linear resonators are a good scheme for coupling them. So that's all these sort of gray bars are things that couple nearby qubits to each other. They also need electrical structures specific to read out the qubits. That's these sort of squiggly structures, also like you saw on the chip picture. But most scary from the point of view of those who build quantum computers is that every one of these yellow squares indicates a place where information should flow in and out from the outside world. So in this concept, basically, each qubit should have 2 inflow or outflow locations. And that sets a scale for the working quantum computer. Now, as I said, these inputs and outputs, they can be optical, using optical fibers, let's say, or they can be electrical cables, but they have to be something. And they have to be something very carefully engineered, very precisely engineered, with low noise in mind, with very low temperatures, very precise control. Now, where this is going, IBM says that they have indeed proceeded along over the years, and they now foresee that they could go far beyond 1,000 qubits. That's what this last but very indefinite milestone for the current years, the next few years, is that they say possibly, say 1K, meaning beyond 1K, beyond 1,000, but also maybe up to 1M, meaning 1 million and plus beyond qubits. And they have some concept for how to do that, but, well, it's rather unclear how much of that they will do in the next couple of years. But just to give you a perspective of what they've done and what other organizations have done as well, but they've been very open about it, so I think this is worth praising. That this is about 5 years worth of advances in their chips. 5 years ago, they had a chip called Falcon, which now I don't remember the count of it, but you see it in the lower right here that that's something like 20-some qubits, according to the connectivity shown here. But the year after that, they had Hummingbird, twice as big, the yellow patch here. The year after that, they had Eagle, another factor of 2 or more actually, I guess in numbers of qubits, perhaps a factor 4. And then the following year, they had Osprey. And now this year, as of now, they have Condor. So almost 1,000 qubits. That is the entire, basically, background of this is the size quantum computer, the gate array quantum computer that they have now in their laboratories. Now, I understand their next step will be backwards. That is, these are impressive in the numbers of qubits they have. They're not super impressive in the quality of operations, the thing we call fidelity. And so they're going back to the drawing board and going back to smaller structures, but ones which achieve new fidelity goals, which make it possible to run longer algorithms, but also more exciting, perhaps for people like me, that makes it possible for digital error correction to start becoming effective for these quantum computers. And we have always felt, and well, always for the last 20 years, have felt that that is the way that finally we will get to really scalable quantum computing, is to achieve the conditions where error correction is possible. And I'd say we're getting close, but puts heavy demands on every aspect of the system to make it work extremely precisely, actually as an analog device, in order that finally digital error correction can be effectively used to make quantum computers do algorithms of essentially arbitrary depth or length, if you will, numbers of gates. Okay, so let me now step into my sort of historic mode. I started very generally, and now I talked about what's the present. Where did this all come from? So as I hinted at the beginning, I would say there were really multiple starts. What everyone always says is that it started here. So here's a paper. Actually, it's more or less the transcript of a lecture given by Richard Feynman. Lecture was in 1981. The published paper, 1982. And sure enough, this lecture has indeed many speculations or thoughts about the possibility of a quantum computer. So one can certainly point to this and say, yes, this is where the story got started. And I will definitely acknowledge that Feynman, this was an important impetus to the field, and rewards rereading. I recommend this as very interesting reading to those of you who wish to understand the basics of this subject. But I will say that this was, first of all, not actually the beginning. So here are some important long ago workers. And so I said, for example, that for me personally, the timeline begins with 1960, and this begins with Landauer, who understood some very basic things about information carriers, and in particular, how they would or would not consume energy. And it was his insights that told us that maybe we don't need a dissipative device to do computing. What I also mention here, are the very notable contributions of scientists in the Soviet Union, and more particularly of the work of Yuri Manin. And those of you who are Russian-speaking could find some real surprise in the text that I have partially shown here. If you really want to have the page, I can send it to you, but who articulate several years before Feynman quite clearly what the point is of quantum computing: the large vector space, the possibility of controlling wave functions in that vector space. He actually had quite a cogent, abstract, but definitely cogent idea of what a quantum computer would mean. Now, this work was little known outside the Russian-speaking world, but, well, now we can see that if you really want to point to originators, that maybe one should point to Manin. On the other hand, the growth of quantum computing was not all that fast after Feynman's lecture either. That he himself did a little bit further work, and I just show a line of mathematics here to indicate that, yes, he didn't merely speculate. He wrote down a few theories for what a quantum computer might be like, and those have been important. They were not revolutionary. He actually rather missed the point that quantum superposition was the essential aspect of quantum computing. So he really failed to notice that. But he did introduce ideas that led, on the one hand, to new ideas for the so-called complexity theory of quantum computing. And I definitely credit Aharonov for carrying this forward, in conjunction also with Kitaev, who had many other insights into what a quantum computer could mean. But this was only many years later. That is, Feynman unfortunately passed away in the late 80s. So his last writings in this were in the mid 80s. And it was in fact many, many years until these ideas came up again and came to the fore. Now, so indeed, I would say it took about, well, on my timeline, about 12 more years before really exciting things started to happen. And so I'll jump in my timeline up to this year, 1995. And at this point, in my view, things were really happening. That is, if you ask me, when did quantum computing start? It was right around this time, because this is where the rather abstract ideas of Feynman, or, well, Manin perhaps, got turned into a set of concrete and very exciting ideas. This was among the first international conferences that took place, gatherings of people who were really primarily concerned with quantum computing. And some really exciting results were discussed at this meeting. I was there, there's the young me, but the factoring algorithm of Shor had just been discovered. And of course, I'm pointing to Shor in this picture. He's rather dim in this little side panel, but the discussion of his algorithm was certainly a large part of this meeting. But I've already mentioned the contributions of Dorit Aharonov and the beginnings of quantum complexity theory. There was Seth Lloyd, who was already speculating about using spins to make a quantum computer. I can point to, except I keep losing my pointer, here it is. There's Barbara Terhal, who introduced the thing called an entanglement witness right around that time. I dropped down to here. This is Tommaso Toffoli. Toffoli, the Toffoli gate of quantum algorithms, was introduced by him. And many of the co-authors, I don't know how many, but I didn't count, but there's Bennett, there's Joseph, the originators of quantum teleportation. So among the foundational concepts of quantum communication was very much discussed. I think I see 2 or 3 more of the 6 authors of that paper at this picture. So this was indeed one of the high point academic research conferences of my entire career. And, many, many exciting concepts were launched at this meeting that kept us busy for many years. Now, actually, rather absent from this were people who really knew how to build quantum computers, I would say. But still, there was very much speculation at that time. And I'll take you through a few of the considerations of what was going on. That is, I would say initially, mostly from theorists. There were actually now many ideas. I mentioned Seth Lloyd, but in fact, there were many other ideas that all came to the fore within a few years. And I don't think I'll read through all of these. They include things that remain very active to this day as subjects for quantum computers: ion traps, neutral atoms, nitrogen vacancy centers, small Josephson junction devices, so superconducting devices like what I was featuring, and spins. But some of these also look not so familiar. The electrons on liquid helium has not taken flight, definitely. And let me also comment on nuclear magnetic resonance that leads the list, actually, because I'd say for quirky reasons, or I don't know, not absolutely the best scientific reasons, this was indeed the method that took flight very quickly, that some members of the group that I just showed you got very interested in this and felt that they could go into the laboratory and do work quite quickly to do quantum computing on the nuclear spins of molecules like this. Now, actually, the factoring of 15 came a few years later, but not many years later, on this precise molecule. And so that was viewed as an important achievement. And there was a lot of attention to this. They said, a simple instrument, you just make a sample, you put it in there, you measure, you don't need a lot of cables, you just need the kind of readout system that normal magnetic resonance instruments have. And definitely these things taught a lot about how quantum computing would be done. But I can say that I was, at this stage, I'll think, this is the late 90s, I was rather resistant. I felt that this was actually not a good start to quantum computing. Maybe the important phrase is the one that I state here: not scalable. There was really no good concept for how this would ultimately be scaled. There were practitioners that thought maybe there would be, and they probably also said, well, it's not so important. We're just at the beginnings of this. Let's just try to get where we can get and see what will be next. But I was not so confident that that was a good approach. On the other hand, we had the example, let's see, let me go back, let me skip something. We had the example of ion traps already in this work, or this is 2 subjects that were scientifically very active in that time, in the 80s and 90s, and then ultimately were awarded the Nobel Prize in 2012. But they were indeed about controlling qubits in our current language. That is, in one case, the controlling which energy level a beryllium ion would be in, what electronic energy level when held in a trap, or alternatively, what energy level of a Rydberg atom an atom would be in when controlled inside a cavity. So these were already known methods. Now you could say, well, were these the basis of scalable methods? In the form that they existed in the original experiments, no. What influenced me very much was the fact that there had been actually a meeting in the preceding year. I had shown you the 1995 meeting, but there was even a meeting even smaller in 1994. And this, I would say, was the entire set of world researchers who cared in 1994 about quantum computing. It was definitely not a very large crowd. But I bring this out because this shows, in addition to some faces you would still recognize, a few that were not at the 1995 meeting, those being, again, if I can get my pointer to work, this is Peter Zoller, and his colleague, even less visible here, Ignacio Cirac. Now, some of you know that Cirac and Zoller produced a very nice set of ideas of how and the ion trap, as it existed in the year 1994, would actually work as a quantum computer. And in fact, they revealed these ideas exactly at this meeting in Torino, in Italy. And that definitely resonated with my thinking as well. The magnetic resonance didn't resonate, so to speak, but their ideas for the ion trap definitely did. And it got me thinking almost immediately that, well, there must be something general to this. And I began some studies, first of all, of saying, well, surely we have to take a very broad view of what could quantum compute. And this is in fact my own first paper in quantum computing, and it had a table of possible entities that might quantum compute. And some of them, I would admit, are kind of weird and definitely not, in play nowadays. The Mössbauer nucleus, definitely not. But other things like electrons in gallium arsenide, yes, became a pretty important thing, but also nuclear spins, also trapped ions, although indium turned out not to be the preferred trapped ions. I had my own sort of Gedanken apparatuses for what a quantum computer might be based on scanning force microscopy, which is better left sort of unsaid. But what I realized in doing this was that, well, yes, there is something really systematic behind this, or something actually fairly universal. And it was that within those years, and then in its final form, as I wrote them in the year 2000, were these criteria. Now, I'm not going to spend a lot of time talking about these. I wrote them up very carefully as a chapter in a book, and that's the version that you should all read if you wish to. However, this is cut directly from Wikipedia, and whoever made the Wikipedia page did a great job. In particular, they used exactly my phrases for these, which I felt was important, rather than paraphrases. But more importantly, have a whole paragraph of descriptive text behind each of these criteria, because these should be read carefully. I mean, the careful choices of words were made, and then I gave explanations for why, and then also sneakily said, well, look, the NMR quantum computer surely can't do this, that they really had no good way of initializing the state of qubits to a simple fiducial state. So to me, that was actually a killer for that. But I also acknowledge that the Cirac and Zoller approach to ion traps checked all 5 boxes. So they definitely had effectively thought through each of these 5 criteria and had answers to all of them. And so when I did subsequent work, for example, on quantum dots, I really tried to make sure that these would be satisfiable, and they weren't always in the ways expected. For example, there's the statement that, well, the decoherence times should be long-lived. And when Daniel Loss and I said, we think that electrons in gallium arsenide, their spins would be very long-lived and would be a good qubit, we missed part of the physics of the nuclear spins, the other nuclear spins in the gallium arsenide lattice. And that's caused years of work. And finally, electrons in gallium arsenide are not actually the preferred qubit, quantum dot qubit, largely because of criterion 3. But luckily, there's an alternative, and there's very active research currently on electrons in silicon or silicon germanium structures. All right, so I'm actually rather near the end. Indeed, I wanted to leave a lot of time for discussion. I want to acknowledge that there are many ways of writing criteria for quantum computers. I've been asked if they should be updated, and I said yes, but not necessarily by me, because they should and have gotten much more specific. That is, well, what are the criteria for a superconducting processor to work? Well, you have to get way more specific about, well, you have to do quantum gates, and they have to be universal, and they have to be very precise. That was sort of understood. That is, in the year 2000, when I said decoherence times, I also meant other things, contributing to the imprecision of qubits. And boy, there's a huge amount of knowledge and lore and, things that have to be checked that make it possible to really satisfy the detailed requirements for that processor. And then for a photonic quantum computer, the requirements are completely different. The ability to measure the qubit, to measure the state of a photon, is key and difficult, and definitely a problematic part of making an all-photonic quantum computer. Let me move, though, to, I like to, do honor to another thinker who I think, while he was not present at the early stages, well, in a sense was, because David Mermin developed very original ideas about how you test for quantumness in the form of Bell inequalities, or the violation of Bell inequalities. But he wrote a beautiful book about quantum computers, which in its body is a nice, excellent undergraduate textbook for teaching quantum computers to a broad set of students. But his first page has some very beautiful, observations, and I won't read them all to you, but maybe I can just feature one or two of the words here, that because it's, in a sense, the last sentence that encapsulates the real difficulty of making a quantum computer. In a quantum computer, the physical systems that encode the individual bits, quantum bits, you might say, must have no physical interactions whatever that are not under the complete control of the program. Now, in retrospect, this is a little too harsh. That is, if it were really true, no physical interactions whatever, then we could forget about it. That it's there's no such thing in physics as no interactions. But controlling them so that they're at a very, very low level, yes, true. And that is the extreme difficulty of making a quantum computer. I'll close with some just sort of aphorisms in some sense. Oh, well, no, I'll indeed say that, of course, we've turned the corner, but this was already a long time ago, that we don't anymore have gatherings where there are 20 people and they're the only ones who care about quantum computers, that we've been filling vast auditoriums with quantum computing enthusiasts, but already almost for 20 years. But the sort of phase transition of that indeed occurred in this period from the late 90s to the early 2000s. But of course, nowadays you could fill a whole Congress hall with people interested in furthering the science and technology of quantum computers. Here are a few thoughts to leave you with. Bennett, who was the forefather of quantum communication in the form of quantum cryptography, also quantum communication, has really a theorem that says that computation does not actually require consumption of power. That's a beautiful insight, however, not confirmed or not borne out by our current use of power. I think this statistic of 2% electricity consumption is a bit out of date, actually, that our use of power, really electric power in running computers, is quite huge, despite Bennett's theorem. And another thinker of that time, of some time back, Margolis, observed and had mathematical models that said quantum computers could operate autonomously. But actually they don't, and the ones that we know how to build are heavily under the control of external agents. And to me, it's understood that a working quantum computer has perhaps more than a passing resemblance to a detector at a particle lab. This is not by no means the biggest one that exists in the world. This is one that's, I guess, been decommissioned at Fermilab, but it also has a vast amount of basically classical electrical technology surrounding a quantum core. And that's kind of looking like what a quantum computer will continue to look like into the future. So anyway, thanks for your attention.